Okie dokie. So, do you guys have this slide next? Good. Okay. So, the concept of solubility has to do with these asterisks, not entirely with these asterisks, but anytime somebody's looking at the solubility of something, they are basically trying to get two unlike things to connect. Solubility. You dissolve something. What are you doing? You're taking a solute and dissolving it in a solvent. Remember those terms? To make a solution, too many S's, right? In doing that, you know what you're doing? And we're going to talk about this in this. This is so exciting. What you're doing, like if it's salt or sugar or something that you want to dissolve in water, basically those sugar particles have to break their bonds because they're stuck together. And then inside. And the water needs to break some of its bonds, and they need to shake hands with each other. It's a wonderful thing. Okay, and then what happens is these new bonds are formed. Okay, new bonds between unlike stuff is formed. Solubility, that's what we're talking about. So when we talk about these 6 different types of ways that stuff connects, okay, the things that are unlike bonds, like the ion dipole and dipole, induced dipole, those two things are reserved for only substances that are different. As I say, two unlike substances, like sugar and water. Okay, but here's the deal: it's quite possible. We'll definitely talk about some situations where you have. I'll just pick on something. It's possible that you're trying to dissolve two things, for instance, that are both polar. Two unlike things that are both polar. When they connect up again, they're going to be dipole-dipole. It's possible that you're going to be connecting two things that are both nonpolar. When they connect up again, that's going to be induced dipole. So that's kind of all it is. But I'm trying to get you thinking about mixtures and what's going on with the mixture. Okay. So of the 6, not 7, but of the 6, those kind of mixed types of bonds, scenarios between polar and nonpolar, those have to be in mixtures. But you could also have mixtures that have hydrogen bonding, ordinary dipole, induced dipole. So just to kind of pick on one of the forces we haven't talked about, because we've talked about pure substances before. Did you catch that? Your homework that you handed in, not this time, but the time before, that was pure substances, when you have a pure compound. Okay? But when you have a mixture, one of the possibilities then is you could have ion, something that is a cation or anion, trying to dissolve it in something that's, what do you think? Dipole, is that polar or nonpolar substance? How many people think polar? Me too. Yep. And I think I have an example coming up. Here you go. So is water polar? How many people think water is polar? Me too. Okay, so water's polar, and this is like a crystalline lattice structure of some ionic compound where an electron was entirely transferred to leave behind the metal as a cation and the nonmetal as an anion. Okay? It could be dissolving salt in water. So water is polar. Those hydrogens, are those hydrogen partially positive or partially negative? Do you remember? Exactly, partially positive. And so you kind of see them partially, they orient themselves. Literally, they do. You're like, really? I'm like, yeah. Okay? So the anion gets kind of surrounded by the positively charged pieces of the water molecule, and the cation gets surrounded by the oxygen, because that's partially negative. Okay? Does that make sense? Yeah. Very good. That was just dissolving salt in water, and how awesome is that? I don't know if you could see, but those the crystalline lattice structure, those alternating cation, anion, cation, those had to break first, and then also the water molecules needed to break each other's being stuck together, and then they surrounded. Then you got a mixture, homogeneous mixture, right? So the other of the 6 that's reserved for just a mixture would be this one, where you have something that's polar, right, dipole, and something that's not polar. You have to induce a dipole on it in order to get it to stick to something. So an example here is this, where I was kind of talking about carbonated beverages. Okay, they're carbonated with gas. Okay, this is an example of taking a gas, oxygen, not carbon dioxide, but O2 molecules, which O2 nonpolar, right? And we can dissolve, the fish need us to dissolve oxygen, gaseous oxygen in water. This is what it looks like. This is when I have a mixture of gaseous oxygen in water. Let's try it this way, because oils, oops. Okay, in general. So then, of course, sometimes we have a structure, and I'm going to pick on acetone here a minute. Sometimes we have a structure that has a degree of polarity, okay? Now, this is actually in your homework that's going to be due Wednesday. You guys are going to get some practice at identifying that. There is definitely a compound out there, and I'm not going to try to name it because I don't have to. But where we go ahead, instead of 3 carbons, let's go ahead and make it 8 carbons. All right? Let's go ahead and make it double bond oxygen. We'll go ahead and even it out with hydrogens. Okay. So what this is alluding to is this. It's possible to have a region that runs around with a certain degree of polarity, but you would probably liken this to an alkane. Now this thing is not an alkane because it has a double bond oxygen, but this part right here is behaving like an alkane. What are alkanes, polar or nonpolar? Nonpolar. Okay, so it's possible to kind of within the same molecule kind of have a little bit of a mixed bag. Detergents are great at that. Detergents are a mixed bag. Okay, they want to be able to kind of unite, dissolve polar things into, nonpolar things into water. So I like this slide because this slide talks about, I told you kind of the breaking up of the solute and the solvent. So think of the solvent as the thing you're going to dissolve the thing in, and the solute is the thing that you're trying to dissolve. So you can kind of, this is an energy diagram. I think we've looked at energy diagrams before along the y-axis. So it takes energy to break both of those intermolecular bonds, the 2 things you're trying to mix. Right? It does. And when bonds are formed, energy is released. Okay, it requires energy to break bonds. Well, once they're we have a couple of, once they're broken, we have a pile of this broken, ready to mix, a pile of this broken, ready to mix. We have a couple of different options. Okay? When it comes time to recombine them, it's possible that the energy associated with the mixture now is less than the energy or the enthalpy or the energy of the individual components, the solution, the solvent and the solute over there. In that case, you have to add energy to make that happen. That's an endothermic process. How much energy you need to add is right there on the energy diagram. If we compare that to another scenario, I'll turn your attention to the red scenario. It's possible that if you look at the solution formed, when you combine the energy associated with your the mixture, okay, your solvent and your solute combined together, it's possible that their energy is less than what you started with. In that case, that's an exothermic process. Energy is released. And this is all consistent with all that other stuff we talked about in Gen Chem 1. Exothermic processes, are they negative or positive? Negative. Endothermic? Positive, exactly. I have a slide, though, coming up. I think it's the next slide that talks about an ideal solution. If the solution is behaving ideally, then basically the amount of energy required to break those bonds, your components, is equal to the amount of energy associated with when those new bonds are formed. And that would be actually the black line, okay, where it's a wash. An ideal solution is this. Basically, the change in enthalpy between your solvent and your solute, before you mix them, to after you mix them, your solution, the enthalpy is the same. So the change in enthalpy is 0. Still takes energy to break those bonds, and energy is formed when those energy is released when those new bonds are formed. And that will be the case if they're kind of similar with regard to what you're breaking and what you're forming. Okay, it's quite possible. That's called an ideal solution. And we're going to talk about Raoult's law in this unit. Okay. And an element of Raoult's law is the solution is behaving ideally. It can happen. You take water. You guys told me water is polar. Alcohols definitely can hydrogen bond. Something that's small alcohol like ethanol or something like that. You figure water and ethanol, and you're going to mix those two, they're both polar, they would love to do that. And so in fact, kind of the bonds that are going to be broken are similar to the new bonds that are going to be formed. So it happens. Okay, but definitely this other can happen too. So solutions that are non-ideal would be like the blue and the red scenarios that I showed you on that energy diagram. They could either be endothermic or exothermic. So we said actually, was it the red one, that the heat of the solution was negative, exothermic? Okay. This would be the case when the new bonds that are formed bring with it less energy than the bonds that were broken. Okay. And then endothermic, this would be the case when the new bonds that were formed have less energy than the ones that were broken. So ideal solution, said to be behaving Raoult's law. We'll talk more about Raoult's law, but it's kind of a wash with regard to bonds being broken, bonds being formed. But non-ideal solutions are just great too. Okay, so let's look at some mixtures. So the things you're going to see up here are the CHCl3. So of course the green are the chlorine atoms, the middle carbon atom, and the lone hydrogen. And we're going to mix it with acetone. Okay. So by golly, if that was carbon tetrachloride, the Cl4C, then it would be nonpolar. But we talked about the fact if you substitute one of those chlorines for a hydrogen, it is definitely polar. The hydrogen will run around with a partially positive, okay, and you can see it dot, dot, dot. That's the intermolecular bond formed with the partially negative oxygen with the acetone. And these are just some different renditions of it. Okay. So again, energy rich, energy poor. This is your Cl3H. And this is your acetone with the 2 methyl groups, carbon, double bond oxygen. Looks like we're making friends. Okay, but this is a mixture. Oops. So like dissolves like with regard to polarity. Molecular polarity, because remember you can have a molecule that definitely has polar bonds like Cl4. But the overall molecule in that case is nonpolar. So molecular polarity, polarity of the molecule. So there's generally what we call immiscibility and miscibility. Immiscible pair, okay, solvent and solute, and miscible. They sound so similar, don't they? Okay, but they're definitely different. So immiscible just means it forms layers. Okay, this forms layers. This would be like your oil and water. And then it gets to be like a density issue, right? The liquid that's most dense will sink, and the less dense liquid will float. Now, it doesn't have to be two liquids. It could be a liquid and a solid, right? You could have a liquid solvent and a solid solute. It could be a gas solute and a liquid solvent, too. Okay, so they are immiscible because they are unlike each other. Okay, unlike molecules. So this is where I guess I should emphasize this. I don't know if this works for you. Something that's polar and something that's nonpolar, they don't mix because of this. Basically, the attraction is weaker. The attraction for the new stuff is weaker than they are with each other. So I've heard it described like this. It's like if you're at a dance and you have the cool kids, anyway, you have the cool kids that are at a dance, and then you have the miscellaneous kids, okay? And the miscellaneous kids are cool. The cool kids are cool. They're all cool, let's just face it. But it's like they all want to be with each other, okay? And these guys are like, I'll kind of do whatever. So it's not that these guys wouldn't go ahead and just mingle, okay? Because they would. These might be polar to me, and these would be non-polar. These miscellaneous ones are like, I'll take whatever. And they are forming tight bonds. And these are like, I'll take what's left over. And it's not in that mix. So that's kind of how it goes. So miscible liquids then, not to be confused with immiscible liquids, miscible liquids are things that do mix, okay? And this would be like dissolving like. Okay. They mix, and everybody's happy if that's what you're trying to happen. Mix, okay. And this would be like plus like. And just a little caveat with regard to energy released or energy required. The solution might be a non-ideal or it could be a wash, in which the solution is ideal. So miscible versus immiscible. And as you might imagine, there's that gray area, right, where it's slightly soluble. It has a slight degree of solubility, and you'll kind of be wrestling that with your homework problems a little bit. So like dissolves like. One of the definitions of insanity is hoping for a different outcome. It works. I don't understand. And then a hydroxyl group. You see we're hydrogen bonds. So, of course, ethylene glycol dissolves in water. So here you can see the mixture. You kind of have to look carefully, identifying the water, and this is the ethylene glycol. So definitely got places to go ahead and hydrogen bond within that mixture. Oil and water, okay. Anytime somebody says, what does that oil look like? You're like, the oil is a bunch of carbon with some hydrogen. Of course, the carbon in this case are gray, and the hydrogen are the oxygen atoms. Oh goodness. The hydrogen are the white balls. Okay, so here you see that it's not that those miscellaneous oil molecules would not mix, okay, but it's simply that these guys are so busy hydrogen bonding with each other that they don't want to go ahead and mix with right, okay. So this actually we looked at before. This is dissolving something that's a crystalline lattice. You can kind of see the large negatively charged anions, the small cations, and of course water's great at being polar. It has something that's partially positive, something that's partially negative, and they connect up quite well. But not all salts are soluble, as you're going to see. Calcium carbonate in today's, the homework that's due for next week. Okay, actually, we did this slide before. Polarizability refers to the ability of something to induce a dipole. And we spent a little bit of time talking about the fact that this type of intermolecular bond basically exists all over the place, whether it's polar or nonpolar. But polarizability increases with size. Okay. So in this case, and I'm going to kind of go back to dissolving a gas like oxygen, nitrogen, and hydrogen in water. Okay. Oxygen, nitrogen, and hydrogen, what they have in common is that those not only are they dimers, right, or they run around buddied up, but also those molecules would be nonpolar. So in order for something like that gas to dissolve in water, you need to induce a dipole. And so that's what's being shown here. Inducing a dipole on a gas such as O2 or H2 or N2, so that you can go ahead and have an intermolecular bond so it stays dissolved. So here's a table that actually has listed by increasing molecular weight those gases at room temperature. And they, because of their different polarizabilities, are soluble to a different degree in water. Okay, oxygen is the highest molecular weight, got the greatest degree of polarizability. So it doesn't look like much, but with regard to mass, you can get 0.00434 grams of water, 0.00434 grams of O2 to dissolve in 100 grams of water. Temperature is a player. This is assuming as at a temperature of 20 degrees Celsius. So notice now when we go to a smaller gas, okay, it's less soluble. And when we go to the smallest gas up there, okay, this is because of polarizability. And put another way, it just kind of goes back to something we've already talked to a little bit, but now it's forming in a mixture. With increasing size comes increasing polarizability. And you're counting on polarizability if you're going to induce a dipole on it. Water's polar, and it can do that. Okay, so kind of finishing up here. This actually is three substances, and I have you can already see, looking ahead, you can see the Lewis structures for these three substances. What somebody did is kind of clever. They basically took water and they dissolved solid I2 in water, and that's kind of the brown stuff. Okay, the I2 did not want to be there, but it's okay. The reason I say the I2 didn't want to be there is because I already see that I2 is nonpolar, and of course the water is polar. Down below there, at a greater density, is pure carbon tetrachloride. Okay. CCl4, even though those individual carbon-chlorine bonds are polar, the centers of positiveness and negativeness coincide in that tetrahedral molecule. Okay, so the molecule is nonpolar. So without further ado, you shake it, and this is what you get. Shake it, give it a little bit of time. And so what you're seeing actually is the I2, and this is kind of a whole different story, and I kind of chased this down one time. The I2 is in, I want to say, different conformations, but the I2 sends out a different color signature, whether it's in water or whether it's in carbon tetrachloride. So the purple at the bottom is the I2, and the reason it preferred the carbon tetrachloride solvent is because they're both nonpolar. And the polar water is Psi all by itself, which just like it wanted to be. Okay, so that's the last thing. We'll see if this works. This basically does the same thing. Oh, we're just big, all right? We'll just go for small.
Solid iodine is not very soluble in water.
On Wednesday. And I had time to look at all of these this time. And they look like this. So I mentioned you won't need to use your calculator this time. Okay. So this first one, just remember like dissolves like, smiley face. So the solvent of interest in each of these cases for number one is water. So basically water is polar, you guys told me. So basically you're looking for which of these. So I went ahead, I went ahead like I've done before and kind of drawn the structures. Come back here. Keep pushing the wrong button. Okay, so like I said, I'm going to post these and make them available. They're pretty straightforward, but notice, for instance, I went with green for the C10H8. So right here, you can see that that is actually naphthalene. And if I was y'all, I'd be like, how'd you know that? And I'd be like, I looked it up. Okay, so naphthalene is basically two benzene rings stuck together, which is kind of fun. Naphthalene actually is question number 2 also. And so I went ahead in that case and kind of said, where you see these purple lines or purple dots, actually that's where your 8 hydrogens are. It's kind of a fun structure. The NH2OH over there in orange, central nitrogen atom, you think it can hydrogen bond? I do. Then the C6H6, that's one we run into before, that's benzene. And again, you know, if I were to pick a different color, you know, where each of the red dots are, those are the 6 hydrogens extending out from the benzene ring. Calcium carbonate. I kind of wish that this one wasn't included in this question. It's not, we're going to talk more about the solubility of solids in water. But if you take plain old chalk, do you think it's going to dissolve in water? No. There's your answer there. Plain old calcium carbonate is chalk, and no, it does not dissolve in water. It's not a very good question, I don't think. So for number 2, basically, you have 2 solvents, not only water, which is polar, but also benzene, and benzene is nonpolar. And so you have A through D, and you're supposed to say which of them is moderately soluble in both. So this is an example, and I think I mentioned this when we were doing lecture. Actually, I still have it up on the board there. This is an example where, to me, you need to look for the union label. No. Look for both polar and nonpolar. Polarity. I'll go ahead and finish it that way. Look for both polar and nonpolarity. So, for instance, to me, are you thinking A? Can you see where you have the hydroxyl group? Brings a polarity to it, but A also has kind of that alkane group. That's basically what I drew on the board. To me, A's got a little bit of a cross functionality to it. Okay, and that's the one only kind of blaring to me. I just answered your homework for you. Dang it, I hate it when that happens. Okay. So, not like you couldn't have answered it yourselves. The next one have these 4 structures. And basically you're looking for something that dissolves in water. See, something that reminded both. Okay. One of the following is got dual functionality. Okay. So I'm going to leave that to you. I can almost see 2. Pick your favorite one that you think of going, oh, I know. No, I think just one. Final answer. I'll let you figure that one. Only 2 more. Number 4. This again is 2 solvents. It says that there's these 2 vitamins. Aren't they pretty? Vitamin C and vitamin E. And one of them is dissolves in water, which is polar, and the other dissolves in fat. And you're supposed to say which is which. So do your best. Look for the things that we said would make those different vitamins polar or nonpolar. And last but not least, did I skip one? Maybe not. So basically, you're supposed to say 2, there's 6 there. 2 are highly soluble in water, 2 are only slightly, and 2 do not dissolve in water. Okay? Voila! Catch you on the flip side. So Wednesday there will be a study session in the library.